Okay, let's continue our third video of chapter 5. In this topic, we're going to show directed weight and bipartite graphs. So in this figure 19, you have the example 1-4 airport shuttle. A large airport has 6 terminals denoted by the letters A, B, C, D, E, and F. So this is what the transfer should use to get from each terminal of this airport. A direct graph G composed of N and L consists of two sets, N different of 0 and L. The elements of N are the nodes of the graph. The elements of L are distinct ordered pairs of distinct elements of N and called direct links or arcs. A direct graph, an arc between node A and node J, is denoted by the order pair I and J, and we say that the link is going in J and outgoing from I. An arc is denoted as Y from A and J. However, we may have A from A to J, it's different from A from J to I. So this is what you can say that it's a different path from one node to another one, from one node to another one. So this is, for example, the dataset 1. You can get this data from the website, and you can see that it's quite interesting and simple as well. So in the Lisa kindergarten network describes 16 children between 3 and 5 years old, and that declared friendship relations. The network given in this dataset is a graph with K equals 57 arcs, and is shown in the figure. A graph reciprocity, that's a measure of the reciprocity between the letters, is around 0.6. So here, for example, what it means? It means that Gianluca is friend of Matteo, and Matteo is friend of Gianluca as well. But when you got this letter here, it means that Juliana is friend of Matteo, but Matteo, it's not friend of Juliana. So it's, of course, it's a peculiar feature of a kindergarten from small children, that I'm friend of you, but you are not friend of me. So it's, of course, it's particular, but it explores some direct graph sets. A direct graph in letter A, and direct B, and a weighted in direct C. So these you have the different section from, for example, you can go from 1 to 7, but you cannot go from 7 to 1. And here you have a different width of each edge, so you can connect the edges but with different weight, right? So a bipartite graph G is N, V, and L, consists of 3 sets, N and V, all of them different of 0, and L. The elements of N are the nodes, and the V are the weights, so you can connect all of these in a similar way. And here's what you have when you have a bipartite, because illustration of bipartite network with N 8 users and V 5 objects, as well as its user projection. So an objection projection, the link weights and B and C are the number of common objects and the users. So here you have the users, 8 items, and here 5 objects. So in this way here you can have some relationship between the users and objects here. So of course in this way you can have some association between the users, and you have some connections between the objects as well. Node degree, some basic definitions. The degree K of node A is the number of edges incident in the node. If the graph is directed, the degree of the node has 2 components. The number of outgoing links, K out, referred as to the out of degree in node, and the number of ingoing links, K in, referred to the in degree of node I. The total degree of the node is then defined as K equals k out plus k in. So the degree sequence is the number of node degree for each node of the complex network. The average degree, denoted by k, of a graph is defined as, so it's the simple average of the graph. And you can do the same as 2 times k divided by n. So here you can use, as an example, compute the node degrees in Lisa's kindergarten. It's a nice example. So here you can use some basic ideas of the network to see some definitions. A walk, WXY from node X to node Y, is an alternate sequence of nodes and edges of arcs. So you can go from node X to any Y. You can use any 1 and 2 and so on. Begins with X and ends with Y, such that you have all of these ends between these two nodes. Usually a walk is indicated by giving only the sequence of transversal nodes. So a walk you can just write the nodes. The length of the walk is defined as the number of edges in the sequence. A trail is a walk which no edge arc is repeated. A path is a walk in which no node is visited more than once. A shortest path or geodesic from node X to node Y is a walk of minimal length from X to Y. In the following will be denoted as P, X, Y. Graph distance. In a direct graph, the distance between two nodes X and Y is equal to the length of the shortest path, Pxy. Connect X and Y. In a direct graph, the distance from X to Y is equal to the length of I shortest path from X and Y, and it means that from X to Y as well. Circuits and cycles. A circuit is a closed trail. That means trail whose end vertices coincide. A cycle is a closed walk of at least 3 edges of arcs, distinct from each other from N0. A direct cycle of length k is usually said k-cycle, is denoted by Ck. C3 is a triangle, C4 is called a quadrilateral, and C5 is a pentagon, and so on. So here, example 1.7, you can make, for example, find a walk of length 5 from node 5 back to node 5. So here you have an answer. You can go from X from 5, and after go to 6, to 4, and after to 2, after 4 again, and 5. Find a trail of length 7 starting from node 5. You can go 5, 6, 4, and after 4, 5, 1, 2, and 4. And after you can go to 5 again. Find path from node 5 to node 2. So you can go 5 and after 4, 3, 2. And find the geodesic from node 5 to 2. You have many other 3 solutions. You can go 5, 1, 2, 5, 6, 2, and 5, 4, 2. All of the solutions, you just need to visit 2 nodes. Find an arc of length 5. So this is the answer that I have just declared here, right? And let's move on. Connectedness and components in a directed graphs. 2 nodes R and J of a direct graph G are said to be connected if there exists a path between I and J. G is said to be connected if all pairs of nodes are connected. Otherwise, it's said to be unconnected or disconnected. A component of G associated with node I is the maximal connecting induced graph contain I. That means is the supergraph which is induced by all nodes which are connected to node I, right? Find behaviors in animals. This is an example. It's quite interesting. So you can use this tool to see if you are take the most important points. Find the shortest route is extremely important also for animals moving regularly between different points. How can animals with only limited local information achieve this? Ants, for instance, find the shortest path between their nest and the food source by communicating with each other via their pheromona, a chemical substance that attracts other ants. So this pheromone is put in the ground, and with this information, other ants can see and can feel the best path, right? Initially, ants explore all the possible paths to the food source. Ants take shortest path will take a shorter time to arrive at the food. This causes the quantity of phenomena on the shortest path to grow faster than on the longer ones, and therefore the probability with which any single ant chooses the path to follow is quickly biased towards the shorter ones. The final result is that, due to the social cooperative behavior of the individuals, very quickly all ants will choose the shortest path. Connecting the components in direct graphs. Two nodes I and j of direct graph G are said to be strongly connected if there exists a path from A to J and a path from J to I. A direct graph G is said to be strongly connected if all pairs of nodes A and J are strongly connected. Some centrality measures. Centrality measures allow the key elements in a graph to be identified. The concept of centrality and the first related measures were introduced in the context of social network analysis. More recently, have been applied to various other fields. Measures of node centrality are the most important: degree centrality and vector centrality and the half centrality. And I'm going to give here some basic information, not all the measures. Centrality measures based on the shortest paths, closeness centrality. Social network analysis originated in the early 20s of the century ago, and focused on relationships among social entities, such as communication, collaboration between members of a group, trends among nations or economic transactions between corporations. This discipline is based on representing social network systems as a graph, whose nodes are the social individuals or entities, and whose edges represent social interactions. One of the primary uses of graph theory in social network analysis is the identification of the most important actors in a social network. So, for example, I have here some marital relations between Florentine families. The graph has 16 nodes and 28 edges. Each of the nodes in the graph is a family, and a link between a pair of families exists if a member of the family has married a member of the other. So, for example, the family Pucci, no one of his family has married with other family here. On the other hand, the Medici family, they got married with many families around them. So the graph interactions in a group primates, the graph with N20 and K31, is an example of a social animal interaction network. It represents data recording 3 months of interactions among a group of 20 primates. contact networks of hijackers and related terrorists of the September 21 attacks. The graph with when n equals to 34 nodes and k equals 93. The nodes represent the 19 hijackers and 15 order associates who were reported to have had direct or indirect interactions with the hijackers. So, for example, here, two socioeconomic indicators of the influence of a Florentine family, such as wealth and the number of pirates, are correlated with the node degree of the family in the marriage network. Just keep attention here. There's just a mistake here. So node degree, right? So there's a space at this point here. So we have wealth, number of pirates, and node degree. As you can see, there is a strong correlation here. The more the health, the bigger is the node degree. Connect graphs and reducible matrices. A convenient mathematical way to describe the graphs by means of the adjacency matrix. The structural properties of a graph turn into algebraic properties of its adjacent matrix. If the graph is connected, its adjacent matrix A is irreducible, while if the graph is unconnected, A is reducible. So, for example, reducible and reducible matrix. A matrix A is said to be reducible if it exists n by n matrix P such that P line times A times P equals this matrix, with A1 and A2 square matrix, and where P is a permutation matrix, that is, matrix such that each row and each column have exactly one entry equal to 1 and all others 0. Otherwise, the matrix is reducible. So, for example, suppose here I have the adjacency matrix. So this matrix is important, for example, to realize some nice interesting here. So, for example, let's take a look in this matrix here. So in this matrix A, we got 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, right? So what it means? It means that the node 1 is connected to 2, and that is direct, so we have the node 1, the node 2 connect to 1. So the number 1 indicates if there is some relationship between the two nodes, right? And here, as you can see, we are going to show you you have some matrices here that you can write the matrix. So in this way, as you are going to see, in a direct graph consists of two components with respectively 3 and 2 nodes. What you got from this matrix? So A line is P34, A P34. This is equivalent to write A line P line 34, A P34, since we have P34 equals to P34. Matrix P34 is an elementary permutation matrix. So just as matrix of connected graphs, undirected and direct graph is connected, strong connect, if and only if its adjacency matrix A is irreducible. These two graphs here, AB, BC, respectively correspond to adjacency matrix AB and AC. The first graph consists of a single strong connect component, while the second one does not. Now let's see this theorem. A real non-negative n times n matrix A is reducible if and only if you can write the identity matrix plus A elevated to n minus 1 is greater than 0. Since compute software is readily available to compute matrix powers, this expression can be easily checked. If any entry of I plus a to n minus 1 is 0, then the contrapositive of the theorem says a is reducible. So let's have a look. If we're going to put the matrix I and B, we're going to make n minus 1, you have this matrix. In A and C, you have this matrix as well. This proves that AB is reducible while AC is reducible, in agreement with the result found by visual expression of the graphs B and C, right? Degrees and edge vector decentrality. The number of neighbors of a node is a plausible measure of its structural centrality. This is because the higher the degree of a node, the more source of information it has available and the quicker the information will reach the node. We can therefore produce centrality rankings of the nodes of a graph based on the following definitions. Degree centrality. In a direct graph, the degree centrality of a node is given by CD is the sum of AJ, where in case the degree node, the normalized degree centrality is given by, so the capital C is the small c divided by n minus 1. A different way to generalize the degree centrality relies on the notion that a node can acquire higher centrality either by having a high degree or by being connected to others that themselves are high central. A simple possibility is to define the centrality Ci of a node I with I1 to n as the sum of centralities of these neighbors. So the centrality C is the sum of centralities of all the neighbors. But it works only when the linear system is defined. In the matrix, equation 4 becomes, so ACE equals gamma CE. The standard way to overcome this problem is to define the centrality of a node as proportional to the sum of the centralities of its neighbors. Bonacci centrality, or alternatively as the edge vector centrality of the node. So this is edge centrality because you can multiply C, and here you have the sum in equation 4. So let the node network given by the logistic map in the form. This is the advanced topics, and it takes from one of the papers that you can have a look. So what it means. Here you are going to see a complex network of logistic map. So this equation 5 gives the logistic map where mi belongs to is in the range of 0 to 4. Consider a connect dynamical network of n, coupled identical nodes given by equation 5. The state equations of the logistic network are given by equation 6. It means that you get here the same equation as 5. So here you have the same equation, right? But you are going to make minus C the adjacency matrix of f of j, where xi key belongs to R is the state variable of node I at time step k, and C is greater than 0, a positive real parameter that represents the coupling strength of the network. Elaborate a complex network. So this is the topic to be done. Elaborate a complex network with n equals 10, mi 3.91, and c equals 2098. Estimate the uncertainty of the calculation in all after nodes after k equals to 100 of iterates. So try to understand, because you are making all these equations together in a complex network, and if you realize this advanced topic 2, perhaps it's a summary of the course, because in such a way you can see the propagation of error in a complex networks. Okay, so this is the last video. I'm very happy that you can reach this stage, and I hope that you enjoy.